Good afternoon, everyone. I'm Jiang Wang. It's a great pleasure to present our work, CNN-RNN, a unified framework for multi-label image classification. This work was done when all the authors was at Baidu Research. The point we are trying to solve is multi-label classification for images. So for these three images, we are just doing single label classification. We are only going to output the most important objects in the images. For example, like airplane, grid pyramid, and arches in the images. But for these three images, there are actually a much richer information in images. If we do multi-label classification, we are going to output this much richer image information, and those richer information are essential for the understanding of the images. For multi-label classification, there are generally two challenges. The first challenge is label correlation, and the second challenge is semantic redundancy. For label correlation, it means that the occurrence of labels are correlated. For example, the label ship has very high probability of occurring with the label seas, but the label ship has very low probability of occurring with the label road. So in order to model this label correlation, the previous model generally use graphic models. So in graph models, so one node usually corresponds to a label, and an edge connecting two nodes have a weight that specifies the concurrence probability of the two nodes. And an inference over this graphic model can achieve multi-label classification that takes label correlation into account. Another challenge is called semantic redundancy. Semantic redundancy means that some labels have overlapping semantic meanings. For example, like the cat, kitty, and kitchen all have the same meanings, and a cat is always an animal. To model the semantic redundancy, people usually use joint label and image embedding. In joint label and image embedding, the labels and the images are projected into the same semantic space, and in this semantic space, similar labels are close to each other, and similar images are close to each other, and relevant labels and images are also close. And by using this semantic joint space, they can model the label redundancy. And we propose a framework called CNN-RNN. This framework is a unified framework that takes both the label correlation and the label redundancy into account. And in this framework, we have to use VEG convolutional neural network to model the images and use that image representation. And this image representation and the label representation are both projected into the same semantic space. And we use recurrent neurons to model the correlation of labels. And by modeling the correlation of labels, we can output one label at a time, and then considering the correlation relationships. For example, in this image, first we output sheep, and then after output sheep, we considering the occurrence of sheep, and then we output C. And finally, we output N, which means we do not have any label to output. The advantage of our method is that first, our method is an end-to-end model that analyzes both the semantic redundancy and label correlation, and our model can train in an end-to-end way, so that we do not need to train each module separately. And also, the recurrent neurons is a much more compact and more powerful model of high-order label correlation than graphic models. And this is our model diagram. So for this model diagram, the upper part is the image representation. The image is input into a deep convolutional neural network to get its representation, and the lower part is the label representation. We use the label embedding to represent each label, and the label embedding is output into a recurrent neural network. And the recurrent neural network can store the labels into its memory and use the state to model label correlation. And the recurrent neural network state and the image are projected into the same semantic space. And finally, a prediction layer is used to output the probability of the labels. And one important trick of our model is that the label embedding layer and the final prediction layer share parameters, so that doing the final prediction is equivalent to finding the least labels in the semantic space. And this is very important for the high performance of our model. So for our model to do inference, we need to output a prediction path, which is a sequence of labels. And this sequence labels need to maximize the probability of these sequence labels given image. But because the recurrent neural network does not have a macro property, we cannot use dynamic programming. And in this work, we use something called beam search. And what does beam search mean? So beam search means that so in each time step, we have a set of candidates, say k candidate. For example, in the first time step, we have cat and person. And in the next time step, we expand this candidate to get more candidates. For example, in the next time step, we have cat and person and dog. And we expand until all the prediction passes have end. And then we got the top k prediction as our final result. And by using beam search, we can efficiently find the optimal prediction path in a structural way. For the training of our algorithm, we use quite standard training algorithm, which use softmax and cross-unit loss, and we use backward propagation through time using RMS prop. But one very important thing of our model is that we need to determine label orders, and in this work, we use more frequent labels to appear earlier than less frequent ones, because intuitively more frequent labels are usually easier to predict, and by predicting the more frequent labels, they can be used to help the prediction of the less frequent ones, which are usually harder to predict. Okay, so this is our experiment. So we did the experiment on two datasets. The first dataset is NUSY. It's an image tag dataset collected by Flickr. And the labels is also the Flickr tags, which are very noisy. It contains two sets of labels, which is tag 80 and tag 1000. And we also perform experiments on MS Coco dataset, which are labeled by human, and the labeling quality is much higher. So and you can see that our prediction result is quite good. The bottom is our prediction result. And this is our quantitative experiment on NUSY dataset. For our quantitative experiment, we have two performance metrics. The first is per class average, precision, recall, and F1. And the second is overall average precision required for F1. And we compare with the joint image label embedding method and the classification method, and also with the graphic model method. And you can see that our method outperforms this method by a large margin, especially for precision. And also for NUSY 1000, we have also achieved very good result on all the three metrics. And also for Microsoft Coco, our results very good. And we also did some experiment to study the recall rate and object size relationship. And we found that as the object becomes larger, the recall rate is even larger. So that means that our method still have some difficulties dealing with smaller objects, which will be our future work. And we also use retrieval to evaluate the quality of our label embedding and image embedding. And in this retrieval result, we use label embedding to find the least labels for each query label. And you can see that the least labels for each query label are highly semantically relevant to the query label. And we also use image embedding and label embedding to do the retrieval in the joint semantic space. And you can see that the least labels for each image are highly semantically relevant to the image. And also, we find that the least label results are usually ranked fine-grained labeled higher. For example, like for the first image, it's ranked hawk higher, but for the classification, it's ranked bird higher. And we also did some attention visualization. So for our image, for example, this image contains two objects, one zebra and one elephant. At first, the attention focused on the whole image, and it's trying to predict the most relevant image. But after we predict elephant, it's focused attention on only the zebra, so that it doesn't pay attention again to elephant. So we did our multi-label classification. Instead of just producing one label, we produced a lot more labels to get much richer information for each image. And our model is a unified framework that uses the advantage of both joint image label embedding and label co-occurrence modeling. And it can also steer its attention to different image regions when predicting different image labels. But for our model, predicting smaller objects is still challenging, and we can use implicit attention mechanism to solve the problem, and this will be our future work. So thank you very much.